These, gentlemen, are aerial photographs of enemy-held objectives. They are our targets for tomorrow and the next day and the next. One of them may be your target. They are the reason for your being here. The reason for all the vast equipment assembled in this and other bombardier schools. For the instructors here to train you. For the pilots here to fly you on your missions. In all likelihood, some one of you now sitting in this room will see one of these targets, not projected on a screen, but moving under the crosshair of your bomb sight. And where will they fall, those bombs of yours? On the runway of this Japanese-held airfield? Or 100 feet off? 500 feet? That will depend on how well you'll have taught your fingers and your eyes to match the precision that has been built into your Norden bomb sight. It will depend even more on how well you will have developed your imagination. Yes, that's right, imagination. Or call it the bombardier's sixth sense, which enables you to move through space at 200 miles an hour, 20,000 feet up, and know second for second exactly where you are in relation to the target on the ground. How about you, mister? Yes, you look as if you were getting kind of snarled up with your homework. Did you ever try imagining what it's like looking down from the other end of that sight line? Well, why don't you try it? That's pretty good imagining. Okay, let's start. Let's figure out just what that bomb sight's supposed to do. Maybe I can help you. That's right. First, you line up the sight on the target. Good idea. That'll do for your telescope. Yes, and then you find a way of measuring the angle between your sight line and the vertical. That's right. That's about it. Only they've rigged it up a little better in the Norden. That pitching and rolling is all taken care of, too. First, there's a gyroscope, which makes it possible to stabilize the telescope in a vertical position. So that no matter how the airplane rolls or pitches, you have a fixed vertical line of reference. Then, to take care of the sighting line, there's a rotating mirror underneath the telescope. You can see that's the same as having the telescope rotate. That means, since the mirror is connected to an indicator, we can see just how fast our sighting angle is closing as we approach the target. All right, what else goes into your diagram? First, altitude. Only put it down as disk speed. I'll put it down that way for now. You'll figure out why in a minute. And you know your airspeed. That's constant, too. So that tells you how far behind the airplane your bomb will fall. That's your trail. Subtract trail from your whole range. That's how far the airplane travels after the bomb is released. And you have actual range. That means you've got your range angle, the most important thing of all. Because when your sighting angle equals that range angle, that's when the sight releases the bomb. In other words, if we can only set up that range angle inside the bomb sight, we will have solved the range problem. There. How do we go about setting it up? Well, first there's our vertical line of reference, which the gyro stabilizes for us. What's that sighting angle? Notice how it speeds up as it closes to zero, instead of moving down at an even rate like a stopwatch. Now, suppose the distance from A to B is the whole range. Forget trail for the moment. Even though the sighting angle does speed up for a given altitude and a given speed, there can be only one specific rate of closing. Find that rate, and from it, the sight will compute the range angle. But wait a minute. You only turn that mirror by hand when you're first trying to locate your target. Look. There's a disc inside the sight, rotated by a constant speed motor. Once you get on the target manually by turning your rate knob, you move a roller toward or away from the center of the disc. The further from the center, the faster the roller turns. That means the telescope mirror is driven faster or slower according to the position of the roller. You turn your rate knob backwards or forwards until you've found the rate of drive, at which the line of sight will stay on the target by itself. It's from the position of the roller when this is accomplished that the sight computes the range angle. You've done all this merely by adjusting the rate knob to keep the crosshairs on the target. But does the rate index now give you the correct range angle? No, it doesn't, because you haven't allowed for trail. You allow for trail before you attempt to synchronize. That's what the trail arm is for. When you start your run, you've already set your trail at the correct reading for your airspeed and the type of bomb you're using. By doing this, you move the roller independently of the rate indicator. Since this means you speeded up your rate of drive beforehand, this calls for a different adjustment of your rate knob and rate indicator to achieve synchronization. In other words, before we start measuring our rate of angular closing, we preset our rate mechanism to allow for the difference between whole and actual range. Does that take care of everything? What's the matter? Oh, the disc speed. Well, that's very simple. The lower, the faster. Yes, that's what it amounts to. You can figure it out for yourself. Remember, we're dealing in angular velocity, the rate of the closing of the sighting angle. Suppose that represented an airplane flying at 10,000 feet altitude. Now, suppose you were flying at only 5,000 feet, but still at the same speed. In that case, you have only half as long for the sighting angle to close to zero. Therefore, the rate of closing must be twice as great. In other words, the angular velocity of closing varies inversely with the altitude. So, before you try to synchronize, you set in the proper disc speed for the altitude you're bombing from. Then, when you clutch in and synchronize with your rate knob, the Bombsight gives you the correct rate angle setting for the particular altitude at which you're flying. After that, the Bombsight does the rest. Including this. So now you understand how the range problem is solved by the Bombsight. But what about... Hey, where are you headed for? I get it, mister. You're going to put that imagination and a few gadgets to work figuring out the course problem. That chair behind the desk will help out. Yes, try your imagination on that. And there's your airplane. And your target. What about wind? Okay, that's your wind direction. All right, here's the starting point of your bombing run. When you want to move the sight line, you move the telescope. When you want to change your heading, you turn the chair. Sight on target, then shove off. Aren't you going to allow for that wind blowing you off course? Now the fore and aft crosshair on target. Well, you been? You'd have quite a time synchronizing on a course like that, wouldn't you? All right, go back to where you started. Now look at the line in the flooring. That was your sighting line when you started. It goes straight to the target. I know, when you're up in the air, there aren't any nice, convenient lines drawn on the ground to help you. Your bomb sight, though, gives you the equivalent of them. Remember how the sight's made in two parts? Underneath, there's the stabilizer. And in that, there's another gyro, only it has a horizontal axis. Above that is your sight. The stabilizer is fixed in the longitudinal axis of the airplane. But you can keep turning the sight so that it's always pointing at the target. But the sight is also connected to the stabilizer by rods. By these, the gyro controls the position of the sight so that no matter how much the airplane yaws, the sight will always point in the same direction. But, and this is what's important here, the gyro gives you a constant reference in azimuth. Let's see how it works. Suppose you're coming onto the course from there. You haven't got your gyro clutched in, so you simply point the sight at the target. You have the target under the fore and aft crosshair, so you clutch in the gyro. Now go ahead. Only don't forget the wind. No. Remember, your gyro is holding your telescope in the same direction you started with. Parallel with the floor lines. See what's happening? You're drifting downwind. Exaggerated here, of course, but that's what you'll see through the telescope at the bomb sight. The target moving away from the vertical crosshair. So what do you do about it? That's right. You turn the sight back toward the target. And by doing that, you're automatically telling the pilot to change the heading of the plane. That target's still drifting off. That's because you turned the sight and the airplane the same amount. The only way you can kill drift is turn the airplane farther than you turn the sight. Try it. Never mind keeping that telescope on the target. Get your drift killed first. There you are. Hold it. Don't change the angle of that telescope. Just lower it the way it is. See the angle it makes with your heading line? That's the same, isn't it, as the angle with the reference line which the gyro has been holding all this time. Well, that's your drift angle. The angle you must set up to get on a collision course over the target. All right, suppose you're in that plane again. And imagine there's a plane just below you on a bombing run. Okay, here's what it would look like. There it is, and you can see its ground track. All right. The bombardier picked up the target, and he's clutched in his stabilizer. Now, suppose he uses his turn knob to correct for drift. That means he turns the sight and the airplane equal amounts. Well, that didn't get him anywhere. You can see he's still drifting. So now he turns the plane faster than he turns the sight, until finally his sight line and his ground track coincide. In other words, he's established the correct drift angle, and he's on a path parallel to the collision course. Are you worried about not being on target, even though you killed drift? Well, on a real run, you wouldn't have gotten so far off. All right. Once you've killed your drift, how do you get on the target again? Well, simply turn the sight and plane equally. That way you won't affect your drift angle. Hey, you dropped that bomb a long time ago. Now what? You don't miss anything, do you? Not even cross trail. But you're right. That bomb will fall trail distance behind the plane on the line it's heading on. So what do you do about it? Yes, that's the course you should have been on. Upwind of the target and parallel to your collision course. But how are you going to get on it? You can't just guess at the cross-trail distance. There's a formula for it. Cross-trail equals trail times the sine of the drift angle. Well, you don't have to worry about the mathematics. The sight takes care of that for you. Look. There's a plane flying over the target on a collision course. You can see where the bomb drops. Cross-trail distance downwind. And here's another plane, coming the same way. Only when it starts to set up its drift angle, it begins to head further upwind. Until finally it's on a course parallel to the collision course, but cross-trail distance upwind. How was that done? Let's see you try it. No, that's not it. Steering for someplace upwind won't do the trick. In the first place, that would throw off your drift angle. Besides, how would you know where to head for? Hold up that telescope again. Now move it as if you were adjusting it for range. All right. Now for direction. Now notice one thing. As long as you kept that bar horizontal, that meant your line of sight was always moving in a vertical plane. Well, suppose you tilted the telescope to the side. That's the way. And that's exactly what the Bombsight does. It automatically tilts the telescope so that to stay on the target, you have to move cross-trail distance upwind. All right? Now try another run. Now change your heading. Only this time, tilt your telescope as you do it. You've got your drift killed? Now get back on target. Okay, bombs away. See how it works? That tilt in the telescope brought you just the right distance upwind. And yet your drift angle wasn't affected. Well, that's about it, mister. Think you've got it all? Range problem, setting up range angle and releasing when the sighting angle matches it, killing drift by setting up a drift angle, and tilting the optics to allow for cross-trail. The sight does that one for you. Looks like they're getting ready for a class in here. Well, you're jumping the gun a little bit there, but let's look. What's the matter? Doesn't it seem so simple now? Well, don't let it worry you. Sure, you'll have to learn what all those knobs and switches are for. But it's still the same question of when to drop your bombs and how to get on course. Once you've started on the run, all you need to use are these two sets of knobs. The course knobs and the rate knobs. That's right. That's what it amounts to. And as soon as you finish ground school, I'll be around and prove it to you on the trainer. How about it?